Did we figure out how to plug something in? All right. Okay. So I hope to finish up 7.5 today. We talked about partial fraction decomposition yesterday and kind of reviewed that. We talked a little bit about the logistic differential equation. And so we're going to do a couple examples with that today. So let's start with page 374, number 34. If somebody would read it for us, please. Bless you. Okay, so let's just stop right there. Okay, so this is a logistic differential equation situation. We have an equation for the for the logistic differential equation, which says that dP is Kp times m minus p. So when you're doing a problem that's going to have to do with populations, it should be pretty clear that this is what we're talking about from the way the problem is worded. The first thing I would do is probably write down the formula that I have here in red, which is the general format. And then make sure that the equation that you're given is in the same format. Okay? Because if it's not, then you're going to try to apply things to the solution and it's not going to work. Okay, so if we compare these two equations, what's K going to be equal to? (0.004), and remember that that's our growth rate. And then what's capital M equal to? 250, and that's the carrying capacity. I was going to say because I spoke about this yesterday. Okay, so remember that when we're looking at the logistic differential equation, that the function kind of levels off up there, and that's going to be where our carrying capacity is. That's that maximum value, that place where the growth and the decay and the resources and everything kind of all come into equilibrium at a single value. Okay. So, what does part A ask us to do? Okay, so that means that we want to find a formula for P as a function of T. And if this is a logistic differential equation, according to our notes from yesterday, what's P equal to? What's the formula for P? Okay. You have to memorize that. That's not going to be given to you. Yeah, this one in particular, I mean, you could probably figure out how to solve a exponential growth or decay problem. In fact, I have quite confidence in you to be able to do that. Um, but this one would take a lot of work for you to get to. Okay. So we've got some of our values here, K and M. So we can rewrite this again. Our carrying capacity is 250. We've got 1 plus a e to the negative. M is 250. K is 0.0004 t. And maybe somebody could do that math for us, 250 times 0.0004. So negative 0.1 t. That right? We got it? 3. Excellent question. It's a constant, but we need it. We're not done. Okay, if we don't know what A is, we aren't finished with what we're trying to do. So how might we solve for A? Okay, so if we have some kind of initial condition, some kind of point, as Zoe says, that gives us a time and a population. So Sarah, what do you think we've got? Okay, so 1970, if we let t be equal to 1970, that assumes that we've started this lowland gorilla thing when in the year 0, which is kind of weird and probably not true because I'm imagining the gorillas were quite much more mobile back then. Okay, so let's just let 1970 be year 0. Okay, and decide that we're going to start our clock then, and then any other time that we come up with, we're just going to have to add that to 1970. Okay, so if we substitute that in from our equation up here, that gives us 28. On the other side, we've got 250 over 1 plus, effectively, a times e to the 0. And we know that e to the 0 is 1. So this is going to give us 250 over 1 plus a. Sure, if I cross multiply, I get 28 times 1 plus a is 250. 1 plus a is 250 over 28, over a is 250 over 28 minus 1, which is what? 7.9. Is Gianni right? Okay. So that means that my equation here is P is equal to 250 over 1 plus 7.9 e to the negative 0.1 t. Remembering that t equals 0 in 1970. You don't necessarily have to write that down. I just want to make sure that we remember that that's what we're doing, because I think that's going to be part of part B. What do you need, Sarah? All right. So I'm just going to copy that formula over. I hate it when that happens. Oh, well, it just bothers me that the blue box is around it, but it'll go away eventually. Okay, so what does part B ask us to do? Okay, so if I take this formula up here and I substitute in 250, so I've got 250 is 250 over 1 plus 7.9 times e to the negative 0.1 t. Okay, right? Because that's what it's asking me, is find the time when my population is equal to the carrying capacity. Okay, so what I've done is I've substituted in 250 for P. What's the problem here? Well, we can follow some, what can I do? When in doubt, what do I do? I do some algebra. What kind of algebra can I do here? Numerators. Well, but I can't. But I've got 250, so that becomes a 1, and I have 1 over 1 plus 7.9 times e to the 0.1 t. Yeah, I could cross multiply. Yeah, but I might as well get rid of my 250s first. So I've got 1 plus 7.9 e to the 0.1 t equals 1. Just think about it for a minute. Well, let's gather our constants, shall we? Which I think is where Pri is going. I mean, you should look at this and go, eh. Not everybody's going, eh, yet. Okay? Not everybody, this doesn't bother everybody. Yes. No. Or a negative number for that matter. So the problem is I have 1 over here and 1 over here, which is great because the last time I checked, those are equal to each other. Which means that this thing has to be equal to 0. Hang on 1 minute. Okay? Because there's a point here. And then there's a solution. So, of course, I can divide both sides by 7.9, right? Because 7.9 will never in a million years be equal to 0, so I can divide by it. Okay. So that leaves me with e to the negative 0.1 t is equal to 0. And as Zoe exclaimed, e to the anything can never be equal to 0. I could kind of make this e to the 0.1 t. I could move it, right? Because that's a negative exponent, so I could move it to the denominator. And if I did that, now when you look at it, what does t have to be equal to make that even have a chance of working? Not 100. No, e to the 0 is 1. Then I'd have 1 equals 0. It would have to be like infinite, which is why there was an arrow instead of an equal sign. Hint, hint, clue, clue, as Mrs. Leas would say. Very good. I love it when people answer their own questions. Okay. So remember what the graph looks like. The graph looks like this. And this is an asymptote. Remember asymptotes? We've talked about asymptotes in like 5 chapters. Okay. So the carrying capacity is a horizontal asymptote that the population approaches, but never really meets until infinity, which makes sense. However, I can bet you comfortably $1 million that we're going to reach the carrying capacity for the number of gorillas. Okay? The number of gorillas, because they're actual gorillas. So I can't have 249.99999999999 gorillas. Okay? Either I have 249 gorillas or I have 250 gorillas. They're discrete things. Okay? So infinity isn't really going to be an acceptable answer. So I'm going to have to think about this again. So I'm going to put my equation back up here. And we want to think about that fact that I can't have part of a gorilla. Either I have a whole gorilla or I have no gorilla. Okay, I can't just have like arms flapping around or something. Okay. Well, and that's that whole average thing. But what I can do is I can play with the math. If I let P be anything bigger than 249.5, that's going to round to 250 gorillas because I can't have half of a gorilla. Okay, so if I do this whole equation using P is 249.5, you could use 249.9. It doesn't matter. As long as you use something that's bigger than this so that it rounds to 250, we can play with the math and we can come up with a time. It's a way to solve the problem because it's a real world problem. Okay. So if I take my equation here, I'm going to let P be 249.5. I've still got the other half of my equation, which is 250 over 1 plus 7.9 e to the negative 0.1 t. And now we can solve for t. So can you solve for t by yourself? All right, then solve me a t. So what does it ask you for? What does the question ask you for? How long will it take? Not in what year, but how long will it take? So you want to make sure that you answer the question you're being asked. So we got a couple people with 82.8 years. What say the rest of you? Yes, I'm seeing some nods. Okay. All right. So we good? We see how this works? Okay. Well, the last problem that I want to do is actually a journal problem, but it's one with a table. So, okay, then let's look at the one with the table. Everybody got what they need off of here? There wasn't really a lot. Did you guys get the right answer in the back? Okay. All right, so let's do page 374, number 37. If somebody would read that for us, please. Laredo, Texas. What about part A? Okay, so let's just start with part A. You don't necessarily have to copy down the table. I just like to point. Okay, so you're supposed to do this using your calculator. So you need to put the data into your calculator for step number 1. And then everybody has the data even if you don't have your book in front of you. And let me grab my calculator. And then if you've got your data in and you go to Stat and you choose Calc, in mine, if you go down to letter B, your option is logistic, and that's what you want to use. Pardon me? Store what? Oh, so that you can, nope, logistic regression. I'm sorry? It should just say logistic regression. Okay. And then your logistic equation is y is equal to c over 1 plus a e to the negative bx, which should look suspiciously like the solution to the logistic differential equation. Your carrying capacity is going to be this c. That was that constant a. So c is equal to the carrying capacity, and b is that km. Okay? If you compare that and the original equation that we wrote down at the beginning of class is the solution. So I get, when I fill this out, actually, I'm just going to round it because it's the number of people. Okay, so you should get something that looks like that too, within reason. Okay, and then what do we have to do? Vars, what do I want? Y bars, function, y1. And then what do I do? My stat plot is on. Oh, but my window is abysmal. You do need like a really wacky window. Yeah, that so did not work. I forget how to do that. Okay, window. 0 to 60, 10. Oh, but I'm going to start with 10,000. All right, so I got my points, and then I'm just going to have to do this old school. Excellent. Okay, so did everybody get a good graph? Okay, your graph goes through your points. Everybody got how to do that? Yes? Okay. So then what does part B ask us? So what does that mean, the population in the long run? Carrying capacity. Okay, so part B is really asking you to find M, which is why we identified what those variables were and the thing that popped off your calculator. So you can look at the solution and figure out what the carrying capacity is. And what is it? Sure, if we go with my numbers. Okay, because it's whole people. I mean, you could make it 232,739.8745, but you're not going to have 0.8745 of a person. I think that's like 7/8-ish. Okay. All right, how about part C? $225,000 people. So basically, you want to know when the population is 225,000. So we're just going to substitute that in and do the math again. So before, well, you can do that. You've got time. So solve for t again. Anybody got an answer? Okay, and then what's the answer to the question? Yeah. Because the question asks us, when does it reach? Not how many years, but when. And so you have to remember that t was equal to 0 in year 1950. Okay, we good? We got it? All right, so what does part D ask us to do? Okay, so we want to go back to our other form. So again, that was why when we wrote down our logistic differential equation that was fit using our calculators, that we compared to our original equation. Because we figured out what m was, right? What's m? Okay, but I need k. How do I find k? So remember that the thing that's in front of the t here, that this thing is actually km. But we just want the k. Oops. So I've got that my 0.101 is equal to km. I know what m is, so it's 0.101 divided by 232,740. And what's my k value going to be? Okay. That what other people got? Yeah? Okay. So now we can write our equation. So we're going to have dp dt is going to be 4.3 times 10 to the negative 7 p times 232,740 minus p. Okay. And that's it. That's all I got for 7.5. You have lots of practice sheets that you can do. The homework is due on Wednesday. The test is on Thursday. I was trying to make it so it wasn't due at the very end of the trimester in case you had other things for other classes, but before the 3-day weekend so that if you were traveling on the senior trip. Well, it's not really a 3-day weekend. It's kind of a 3-day weekend. We've got capstone in the morning and then other things. No, it's next weekend. Okay.